This is the second video I put together for section 2.4 in Precalculus. Basically, I'm going to go through and talk about the way we find potential rational zeros of a polynomial function, and I'll talk a little bit about what we used to have to do and how things have changed. I'll also go through a couple of examples of using synthetic division to help us factor a function. So first of all, the rational zeros theorem basically describes how to take and find what could be rational zeros of your polynomial function. So in finding the possible rational zeros, we're basically finding factors of, or potential factors of, whatever function we're dealing with. What you're going to do is, whatever your polynomial function is, you're going to take the leading coefficient and the constant. The way this works is, if you consider, well, first of all, if they are integers, what you're going to do is you're going to take the constant factors and divide them by the leading coefficient factors. So what we say is we let p be an integer factor of the constant coefficient, that's your a sub 0, and we let q be an integer factor of the leading coefficient. And basically what that means is any factor of p, so any factor of the constant divided by any factor of the leading coefficient is a possible zero of your polynomial. Now, it used to be that we had to use those and kind of use guess and check and try to find the zeros in that way. Well, now we have our graphers, and we can use our graphers to narrow down the search even more. So here's an example. Finding the real zeros of a polynomial function. Write down this function here. First of all, what are the potential rational zeros? Well, there's going to look like there's a lot, because we're going to have to take every factor of 36 and divide every one of those by every factor of 2. So the potential rational zeros, there's quite a few, because both positive and negatives work. Now, we're not going to go through just guess and check and trying to figure all these out, because there's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible zeros. So to lessen the work, we actually are going to look at the graph and narrow down our search a little. Here's the graph. It looks like right here, it looks like perhaps, let's see, this is -6 to 6, so that's, I'm just looking to see what I had my window set at, since there's 3 tick marks and it's -6 to 6. Each tick mark is 2. Well, that tells me that it looks like maybe 2 would be a good number to start with, and that's what we're going to do. So basically what I've decided is I'm going to take and I'm going to divide this polynomial function by x minus 2, and I'm going to do that using synthetic division. So this entire polynomial function, f of x divided by x minus 2, well, I do that using synthetic division by writing the 2 up in the box to the left, and then I write all the leading coefficients out. Keep in mind, you would need a placeholder if we're missing any terms that we could have. So now, if I go through the synthetic division, remember I drop down the 2. 2 times 2 is 4, 4 minus 1 is 3, 3 times 2 is 6, 6 minus 2 is 4, 4 times 2 is 8, 8 minus 14 is negative 6. Negative 6 times 2 is negative 12. Whoop. Negative 12 minus 6 is negative 18. Negative 18 times 2 is negative 36. And negative 36 plus 36 is 0. That's good, because that tells me that x minus 2 is a factor. So now from there, what I'm going to do is I'm going to rewrite this. What I have now found is this function that I had before, 2x to the fifth minus x to the fourth minus 2x cubed minus 14x squared minus 6 plus 36, that can be rewritten. Since I factored out a first degree binomial, the result that I have down here is going to be 1 degree less than this. So this is going to be a fourth degree polynomial. What that means to me is this represents my fourth degree polynomial. So f of x now is equivalent to x minus 2 times this fourth degree polynomial that I have, which would be 2x to the fourth. That 2 comes right here, plus 3x cubed plus 4x squared minus 6x minus 18. Now what I can do is I can graph this remaining polynomial function, or this resulting polynomial function that I got after I factored out an x minus 2. Why would I graph that? Well, to find the zeros again. I could use the old graph, but you know, it's fun. It's fun to see new graphs. So I plug that into my calculator and take a look at my graph, and it looks like it crosses at 2 spots yet. If you remember back, the graph that we had showed it crossing at 3 spots. So I've already factored out one of them, so now I should have 2 more remaining. Just a way to verify that what I'm doing is making sense. So it's kind of hard to tell. It doesn't look like it lands on any one graph, so I can certainly use my zero function on my calculator to help me out. And I want to see what this 0 is, so I'll just put a left bound of negative 3 and a right bound of 0. And it looks pretty much right in the middle of negative 1 and negative 2, so I'm going to guess it's at negative 1.5. We'll see what happens. Oh, we can't have 1.5 there. Let's see what happens. Yes, right again. All right, so the 0 was at negative 1.5. That's good. Negative 1.5, that's the same as negative 3 halves. What I can do is I can put that 0 in my box for synthetic division, and that's what I will do. So I'm checking, or I'm going to try to factor out and verify that x plus 3 halves is going to be a factor. To do that, set it up the same way that I had before. I'm going to put negative 3 halves up here, and then I write the coefficients out for my synthetic division. 2, 3, 4, negative 6, negative 18, and then I go through this process again. So again, I bring the 2 down. 2 times negative 3 halves would be negative 3. 3 minus 3 is 0. 0 times anything is 0. 4 plus 0 is 4. 4 times negative 3 halves would be a negative 6. Negative 6 and negative 6 is negative 12. Negative 12 times negative 3 halves would be a positive 18. That verifies, since this is a 0, that x plus 3 halves is a factor. Now, up here, the degree was 4, so when I factor out another first degree binomial, my result, these numbers down here, are going to correspond to a third degree polynomial. So I'll rewrite that at this time. Remember, I've already factored out an x minus 2. I've now factored out an x plus 3 halves. 3 halves. And now I've got, what I have remaining is a 2x cubed. I don't like my 3's very much on here. Since there's a 0 here, there's no x squared term, so I just have to jump to plus 4x minus 12. So I've got another factor out. Now I'm going to put that into my calculator. So now what you'll find if you graph 2x cubed plus 4x minus 12, hoping to factor one more thing out so you're down to a quadratic, you find that you don't really have a rational, you don't really have a rational number that you can use. This 1.4561642, that doesn't really look like any repeating or terminating decimal, which makes me think it's an irrational 0, which we're not going to be able to work with using synthetic division. So that's about as far as we'd go. So to answer the question, what are all the rational zeros? Well, you would say x equals 2, x equals negative 3 halves, and x is approximately that 1.4, what was it, 245, excuse me, 6 from the graphing calculator. Those would be the rational zeros that you would be able to find. I just want to briefly mention to you this upper and lower bound tests for real zeros. Basically what it says is, if you take and you look at a range on your calculator, you see the function, you see where you think the zeros are. If you want to be sure that there's no real zeros outside of the window that you can see on your screen, you can pick some number to the right, or some value k that's greater than 0. So some number to the right on your graph that's to the right of any zeros you see, and use that value for k in your synthetic division. If in the last line of your synthetic division every number is non-negative, so either 0 or positive, then there are no zeros to the right of the number that you tested. We call that an upper bound of, or upper bound for the real zeros of the function. Likewise, if you pick your number to the left, and it does need to be a negative number or 0, if you pick that value for k and use synthetic division, if the numbers in the last line are alternately non-negative and non-positive, so that's saying a negative number or 0 for every other number, then there are no real zeros to the left of the number you just tested. Keep in mind, you would not be able to use the actual zeros to verify this. You have to go just outside of them. Here's another example of finding real zeros of a polynomial function. Here's our polynomial function. What are the potential real zeros? Well, again, you could take any factors of the constant divided by any factors of the leading coefficient, and those are possible zeros. Compare that to the x-intercepts here. In so doing, you would think that 4 and negative 1/2 are possible rational zeros. There's another, what looks like a 0 right here. However, we don't have another number as one of our options to use. Right now, try using the 0, 4 in synthetic division with this polynomial function. So you're going to put 4 in the upper left box, which means you're trying to factor out an x minus 4. Do that using synthetic division. Once you're done, you should see that it actually is a 0. This tells us the function we started with right here could be written as x minus 4 times 1 degree less. So since we started with degree 4, it's a degree 3 polynomial times that x minus 4, using the same coefficients from your synthetic division. Now use synthetic division again with a negative 1/2. Once you do that, you should find, because this is a 0, that negative 1/2 did work. That tells us that we can take an x minus 4 and an x plus 1/2 out, and since we got a 2 as a leading coefficient here, that would be 2x squared minus 4, which is 2 times x squared minus 2. That's where this 2 came in, and the x squared minus 2. Finally, you can solve this for the other zeros, because x squared would equal 2, so x would equal plus or minus root 2. Here we know x equals 1/2 works, or excuse me, negative 1/2. And from here, we know x equals 4 works. And that's where these answers come from.